I'm starting. Good morning. Just waiting for we'll just wait for one more minute. Right, okay, let's get started then. So we're going to be finishing off our we're going to be finishing off our space topic today, and then after half-term break, you're going to see an assessment, which is one of those multiple choice quizzes, pop up after the half-term break for you guys to have a go at. You have a 2-week deadline to complete it, and like the last one, you're going to have 3 tries. So make sure you get that done within that 2-week period. It's best to get it done as soon as possible, just so then it's out of the way then. Okay, so we have a few learning objectives today that our topics I've broken down into learning objectives. The very first one that I want to cover is what is the difference between, right guys, let's, hang on. So in the chat, let me just let's make sure that we stick to questions and answers. Okay, so what is the difference between weight and mass? Because a lot of times people use these two words interchangeably, meaning people use it in everyday language to mean the same thing, but in physics, they're actually different. So your mass, let me make sure that I have a right color. This color should be good. Your mass, the unit of measurement is grams, kilograms, etc. But this unit of measurement, basically, you can think of mass as like how much stuff makes up what you are. So how much matter or how much stuff makes up the object. Weight, however, is the force of gravity on the object because of its mass. And the unit for weight is in newtons because it is a force. So when people say things like, I weigh 50 kilograms, that in terms of physics is actually incorrect to say. You can't weigh a unit for mass. Your weight is measured in newtons because it is a force, because it is the force of gravity pulling on you because of your mass. So the mass is just how much stuff makes up who you are or makes up the object. And because of this, how much stuff there is, you have different pools of gravity. So something that is bigger, that has more mass, will have a greater weight because of the force of gravity. Now, you might be thinking at this point, right, why does that matter? If they're linked so closely, if the more mass you have, the more weight you have, why does that matter anyway? And the reason why this distinction is important, the reason why we care about the difference between mass and weight, is when we go into things like outer space, such as this topic. Because weight is dependent, as we mentioned, on gravity. So if you go somewhere where there's less gravity, or even zero gravity, even though you have mass, you won't have a weight. So here on Earth, if we're just talking about Earth, yeah, you might be right in saying that the distinction, separating mass and weight doesn't really matter. But when we talk about things in outer space, it then starts to matter because gravity becomes different. Gravity starts working different. Yes, correct, Max. Correct. So like for example, if something is big but it's not made up of much stuff, like for example, low density, if it has really low density and things are more spread out and there's not actually as much stuff that makes it up, then it even though it's large, it might not have much matter. Like if you think about say you're blowing up a balloon, that balloon might be huge, but the matter, the mass, is mainly just the outer edge of it. Okay. So let's put this into perspective of a maths formula. We have this formula here that we use to calculate for weight and calculate based off of the relationship between mass, gravity, and weight. So if you wanted to convert between one or the other, it's a very simple formula. Weight is basically just the mass of the object times what we call the gravitational field strength. Which is it means exactly what it says. It's the strength of the gravitational field. And remember last lesson we talked about what a field was in physics. It's basically just an area where a non-contact force can act. So with a gravitational field, it's an area surrounding an object where the non-contact force of gravity can act, pretty much. So if this field was stronger, then you're going to weigh more. If this field was weaker, then you're going to weigh less, even if your mass is still the same. So if you imagine, let's say you are an astronaut. Here you are on Earth. You're quite big. And your mass was 50 kilograms. So here you are on Earth. The gravitational field strength on Earth at key stage 3, so at year 8, we're happy to take it as 10. The unit is N/kg, so newtons per kilogram. What this unit means is how much force is there pulling on you based off of your mass. Don't stress too much about this unit. This is just a unit we use to measure gravitational field strength, like any other unit, N/kg. On Earth, this is 10. If you do a bit of a Google search on your GCSEs, we use 9.81 to be more accurate. But at key stage 3, at year 8, we're happy for you to just use 10. So I'm going to just use 10 for now. So you're on Earth, your mass is 50 kilograms. How much do you weigh then? Well, from our formula, your weight is just your mass, which is in this case 50, times by the gravitational field strength of wherever you're at. In this case, it's Earth, which is 10. So your weight on Earth would be 500 newtons. That just came from 50 times 10. But let's say that you took a trip and then you went to the moon. Your mass hasn't changed because it's not like you chopped your arm off and then all of a sudden you're made up of less stuff. Your mass is still going to be the same because it's dependent on how much stuff, how much matter makes up who you are. So your mass is still going to be 50 kilograms, but the moon has a weaker gravitational field strength than on Earth. So your weight is going to change. So the gravitational field strength of the moon, you don't actually need to memorize this, it's 1.6. Newtons per kilogram. So once again, what's going to be your weight? Well, weight is mass times gravitational field strength. Your mass is 50 times by gravitational field strength, which is 1.6 in the case of a moon. So 50 times 1.6. I'm not doing this in my head, by the way. I have a calculator, so I mean, as much as I want to brag and have you all think that I'm some sort of mental math whiz, I am not. So I put it into my calculator, I got 80. So my weight is 80 newtons. So this is the principle I want you to understand. Your mass does not change because that's just how much matter makes you up. But your weight will change dependent on where you are. If you're on Earth, it's going to be everyone on Earth has, is the same gravitational field strength that we're all experiencing. But if you are talking about outer space, that weight then changes. Yes, Lucy, that is perfect. Right. Perfect example. The moon is the best weight loss program. So if you ever want to lose some weight, head to the moon somehow. Right. Millie, let's focus on the work, please, rather than the social aspect. I mean, it's great that you're socializing, but let's not spam the chat with unnecessary stuff. Okay. So we have then this distinction because in this topic we're talking about outer space. On Earth, you might think, well, this distinction doesn't matter, but it is a really important distinction to make and keep that consistency. I'm going to move on to the next bit, but I want you guys to have, if you want some extra practice on gravity and space and those calculations using that formula, I do have some on my website. I'll just send you guys the link. I'll put it in the chat. It's under 3. Evan, drop it. I'm going to start muting people if they just start spamming the chat with nonsense. Okay, so if you click on number 3, you will see weightcalculations.docx. So you can open that up and just use that equation. In terms of rearranging it, it's the same as you do in maths where you substitute and then rearrange the equation to calculate for it. At the end of this, I'll go back and do a bit of the maths for those of you who are interested in wanting to practice a bit of the calculations. At Key Stage 3, it's not really as important, but it would be good practice for those of you who want to practice some calculations. The title for this lesson is Gravity and Space. Okay. Now, our next thing that I want us to define is what an orbit is. So, hopefully we have some background knowledge. We would have heard of the word orbit before, like we would have heard the Earth orbits the Sun and the Moon orbits the Earth. But what does that mean and how is this possible? I remember way back when I was really, really young and then learning about gravity, how the sun's gravitational pull keeps the Earth in line, keeps us close to the sun. And I remember thinking, well, if the sun's pulling on the Earth with its gravity, why are we not just crashing into the sun then? I remember being really confused by that. And the reason why, for those of you who had the same exact question as me when I was young, the reason why is because you can think of an orbit as falling but never making it to the ground. Now I have a diagram here that sort of showcases this. If an object was just completely stationary, it would just get pulled straight down. So let's say we had this object here. It's getting pulled down to Earth or to the sun via gravity, right? If it wasn't moving otherwise, then yes, it would just get pulled straight down until contact is made. But in this case, it's moving forward a bit. So it's moving forward at the same time as gravity is attracting it. So that's why I have an arrow by here and a forward motion arrow. So when you have, like in between, a pull this way and then a pull this way, where is it going to go? Well, in between, isn't it? So the actual motion, the direction it ends up, if you just imagine, like, let's say that you had two people tugging on you, one from this side, one from the other side, it's going to end up in the middle. So this purple arrow here is the actual motion direction, as a sort of like a combination between the downward force of gravity and the horizontal motion due to its speed, due to the way it's moving. And then this keeps happening. So on this third diagram by here, I try to show you guys that this keeps happening. So goes this way, and then once again in between gravity and its horizontal motion, this way, this way, this way. And then so notice that there's like a balance between it falling downwards towards the main object, the Earth or the Sun or whatever we're talking about here. So notice that there's a balance between its forward motion and the gravitational pull. And so it's falling, but it's never making it to the ground. So it's falling, but it's never making it to the ground. This is what an orbit is. So an orbit, you can think of it as, let me change color. It is basically a balance between gravity and the object's forward motion until it only goes around the larger object, but not reaching it. So that's basically what an orbit is. When we talk about how, like, the moon is orbiting the Earth, the moon is falling towards Earth but never making it to the ground because of its motion. And in the same case, whenever we try to release a new satellite, like put a new satellite into outer space and have it orbit the Earth, we don't like just shoot it straight up. We try to give it a bit of speed. It needs to be enough speed for it to be locked into this orbit. And this requires a lot of calculation from scientists to work out how fast we need it to go in order to balance out its weight and therefore the gravitational pull towards the Earth until we get this locked balance, and then it just ends up orbiting. So that's what an orbit is. It's that balance between that gravitational pull and that forward motion until it gets to the point where it is falling but never making it to the ground. Okay. So no, not like a trampoline, because if you think about a trampoline, like you jump up, but then you just get pulled straight down. Well, like the moon isn't getting pulled straight down to the Earth. The our satellites aren't just getting pulled straight down to the Earth. When it's in orbit, it's not like go at risk of falling down. It's mainly that balance that we're looking at. So we're looking at like a precise balance between its weight and its forward motion in order to like have it go in a particular direction where it doesn't actually reach the ground and then just does a circular motion around the main larger object. Okay. Now moving on. So, what our next learning objective is, what are stars? Now this is quite interesting because for a long time we didn't actually know what stars were. We didn't even know that there was that our sun was a star, for instance, and that basically the other stars that you would see in the night sky are like other suns. So, stars, they're basically just massive how do I phrase this? Massive spheres of gas / plasma. So for example, the gas that makes up our sun, our star that we orbit, is hydrogen and helium mostly. But because it's so hot, the majority of that gas turns into plasma, which is something that you don't really need to know much detail at this stage, but it makes for an interesting additional point if you want to do any further reading. In that, like when something gets hot enough, it can turn into plasma, but it's still hydrogen and helium, still those two elements. So it's massive spheres of gas and plasma, and because of that heat, it releases a lot of energy, and this energy is released in the form of heat and light. One common misconception, so a common mistake that a lot of students make. One sec. No, because Evan, the moon still has a gravitational pull. There's just less. Okay, so back to stars then. Right, we have massive spheres of gas and plasma. They release a lot of energy in the form of heat and light. Now, when we talk about stars, a common misconception a lot of students have and I'm going to write this out and put a giant X around it. Stars are giant balls of fire. So a lot of students make that mistake and describe stars as being made out of fire. And as you can imagine, this is actually quite an easy mistake to make, because when you look at pictures close up of our sun or of a star, because it's reddish and yellow, you might think, oh yeah, that looks exactly like fire. It's similar to fire in that fire also releases energy in the form of heat and light, so it looks similar, but whereas their composition, what they're made out of, is entirely different. So not fire at all. Chemically, it's entirely different, even though they might look similar. So do not make this mistake. Otherwise, you won't get any marks for an answer like this. Max will be after half-term break. Okay. Stars historically have always been very, very useful for us. Back before like compasses and things were invented, people used what are known as constellations, which is just groups of stars that form what looks like a pattern. And they used to use that for navigation, because because the stars are so far away, the night sky looks fixed. It looks unchanging. So way back in history, before we developed radar, GPS, compasses, people used to navigate through looking at the sky and identifying constellations. So they would set up like patterns that they could spot in the night sky, give it a name such as the Big Dipper, or Orion, things like that, and try to navigate using that as like a fixed point. Kind of like when you're navigating using landmarks instead of a map or instead of GPS. If you've ever tried to navigate using landmarks before, that's how they would do it. Or if you imagine, like, let's say that you were in a forest and you looked at one fixed point in the distance, such as, I don't know, a hill or a mountain, and you think, right, okay, I'm going to just walk towards that point over there. And then you just keep going towards that. So that's sort of what people use constellations for. In terms of like actual physics, the constellations don't actually mean anything. Like, they're not actually a group of stars that have any sort of real combination or any sort of real link. It's just back in the day, the pattern was created. Yes, Millie, very good question. Stars do move, because of the next thing we're going to talk about is stars also orbit. So let's talk about galaxies then. But first I want to put things into order of size. So we have like moons, which we call like satellites. Basically, bodies that orbit a planet. Those are the smallest. Then getting bigger, we have the planet itself. And then a planet, we have a star. And then the star, we have a planetary system. So like, for example, the solar system. And then we have what's known as a galaxy. So let me summarize this. So with moons, they're things, bodies sorry, my mic cut off. Bodies that orbit, oops, one eye there, a planet. And this could be like either artificial, which means it's man-made, or it can be natural, such as the moon itself. Then we have planets, which is, as an example, Earth. So bodies that orbit star. There's a bit more detail that goes into what a planet is, but that's just sort of the gist of it. And then we have a star, which is sphere of gas/plasma, large, that give off heat/light. And then when you combine all of those things, you can get, for example, the solar system, which is a collection of planets that orbit a single star, or stars, because we found some planetary systems where there's like 2 stars. Too many to count. There's like millions upon millions, hundreds of millions of other solar systems. So the reason why we call our system, our planetary system, the solar system, is because our sun actually has a name that's not just sun. Our sun's name is Sol, S-O-L. So that's our sun's proper name in astrophysics, Sol. So we call our planetary system the solar system because it's a planetary system that sort of belongs to our sun named Sol. And then when you have a group of stars, large collection of hundreds of millions of stars, a lot of them with their own solar systems, with their own planetary systems, you get what's known as a galaxy. And our galaxy's name, anyone know what our galaxy's name is? Milky Way, very good. Just to put this into perspective, our Milky Way, in terms of how many stars, so other suns there are, people approximate it to be approximately 250 billion stars as an estimate. So scientists estimate that in our Milky Way there are 250 billion stars. Now this isn't even as far as it goes because you can have hundreds of millions of galaxies and they all then form the whole universe. So the universe is as big as we go. We don't really know anything beyond that, but we just know we have the main universe, and all of this forms universe. And that is made up of hundreds of millions of galaxies, each with billions of stars, and a lot of those stars have their own planetary systems. Not every single one, but a lot of them do have their own planetary systems. And those planets can have their moons. So, I mean, I'm going to put my tinfoil hat on here, but I just think, my personal opinion is that in terms of like extraterrestrial life, Not necessarily how you see in the movies, but I just think, right, the universe is just too big for there to not be life somewhere else. Somewhere. There's also a picture I want to show you guys. There's a very famous picture. It's probably my favorite picture, as weird as that sounds in terms of having a favorite picture. This is my favorite picture. Come on. Let me enlarge it. There we go. Okay. So this is known as the Hubble Deep Field picture. I hope you all can see this. You see all of these bright little specks. You might think, okay, those are all stars. Every speck that you see, including the smallest ones, each of those is a galaxy. Basically, what the Hubble Deep Field picture was is that we had the telescope, we pointed into a specific section of the sky, we had it for a long time, long exposure to get as much light as possible, because when we just take a regular picture, we haven't gotten enough light in order to have that picture form clearly, so sometimes you can't see things, it's still too dark. But because we did this for a long period of time to get as much light from those areas as possible, we formed this picture. This is known as a Hubble Deep Field picture. If you want to look it up yourself, spelled like this. So each little speck that you see, there's a galaxy, there's a galaxy, there's a galaxy. Every single dot is a galaxy. And each of those galaxies have their billions of stars. And a lot of those stars have their own planets. Yes, it is possible. It's definitely possible. It depends on the power of the telescope. For example, we can see that our closest neighbor galaxy is a galaxy called Andromeda. So that's the galaxy that's closest to us, the Andromeda galaxy. And you can actually see it with a telescope. It's hard to tell that it's Andromeda because it's so far away. It looks tiny. You might miss it unless you know what you're looking for. That's a good question. Hold on. Let me check. How can you see Andromeda with personal telescope? Yes, you can see Andromeda with a personal telescope. Yeah. So in terms of like a Hubble Deep Field picture, like this, you probably won't be able to do it because it's like long exposure. But to see Andromeda with a telescope, yeah, that should be straightforward enough to get like a decent telescope from Amazon. But you can do it with a personal telescope. Millie, that's inconclusive. Right. So in terms of how large the universe is, it puts into perspective in like with how small we are. And I think if you want to go on to study something, like if you're interested in studying space, one common thing that I notice with like a lot of students who become interested in space is because the feeling you get from studying space, it makes you feel small in a good way. Because when you like, let's say you're having a rough day, things aren't doing so well, you're a bit stressed out. And then you look at the Hubble Deep Field picture and really, really imagine how small you are in comparison to that. In comparison to just how many other planets there are, how many other stars there are, how many other galaxies there are, it just puts into perspective like how big your problems actually are. That's why this is my favorite picture, because to be honest, I've had many, many times in my life where I think, oh God, I'm, stressing out over nothing. Have a look at Hubble. It's my desktop background actually. Have a look at Hubble Deep Field and just think, okay, Actually, in perspective, I'm very, very small. My problems are very, very small. Look at all of this. Look at all of what is out there. That's my rant. Okay, so yes, Ruben, spot on, spot on. I was gonna mention that, but it slipped my mind. Andromeda is actually in about in 4 trillion years' time. Andromeda is going to collide with the Milky Way. Not everything will be dead, so don't think immediately everything will be dead, but it's basically just going to combine because remember, and like galaxies are just groups of stars. It's not one giant physical thing. It's just a grouping of stars. And when Millie, you asked whether stars move, they do because they move with that galaxy and they orbit the center of that galaxy. So at the center of the Milky Way, for example, it's been theorized that the center of the Milky Way is a supermassive black hole, and that, like, when I say it's been theorized, I say we're like 99% confident that that there's a giant black hole in the center of our Milky Way galaxy, and that all of the stars are basically orbiting that black hole like the Earth orbits the sun. So I don't want people to get scared because we're not getting just sucked into that black hole, because remember, the orbit, we're in a balance. So we're balanced out, we're falling into the black hole but never reaching it because of that balance between our forward motion and the downward motion being sucked in. So when Andromeda and the Milky Way collide, it'll basically just be like a fusion of those two galaxies. The night sky will change, obviously. It'll be hugely different. Millie, to answer your question about what exactly is a black hole, it's basically like if you think about a star that's gotten too big and it just sort of collapses into itself, creating like basically not a tear in space-time, but like an infinitely dense spot that not even light is fast enough to escape. So that's why we call it black. Okay, so moving on then. Right, practice time. Oh, there's one last thing. Sorry, I forgot to mention. One last thing for you guys to know. Defining what a light year is. One last thing. Okay, so as you can imagine, our peasant Earth measurements are not sufficient for outer space. On Earth, we measure things in meters and kilometers. In outer space, because things are so far away, we don't want to be writing a billion zeros every time we measure something. So we came up with a new unit of measurement called the light year. And once again, common misconception alert, because it's light year, a lot of people think that this is a measurement of time, but it's not. It's a measurement of distance. So I'm going to write that out just to clarify and establish. It's a measurement of distance. And it is specifically how far light travels in 1 year. So light is basically the fastest thing. Light is basically the fastest thing. It travels at a speed, so light's speed is about 3.0 times 10 to the power of 8 meters per second. If I were to write this out, this is 3 1, 2, 3, 4, 5, 6, 7, 8. There we go. 300 million meters per second. So that's how fast light travels. And when you let light travel for a year, that distance then is a light year. Just for fun, let's do a bit of calculations and turn this into kilometers. Okay, so light goes into light travels at this speed, 300 million meters per second. So how far is it going to travel in a year? Speed equals distance over time. So distance is equal to speed times time. Okay, so the distance then becomes 3.0 times 10 to the power of 8 times time. So 1 year, we need this in seconds because this is in meters per second. So how many seconds are there in a year? Anyone want to work that out? How many seconds are there in a year? Okay, there's 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 days in a year. So that's around 31536,000. I'm not going to take into account light years, rounded. And then we times those two together. Whew. Times 300,000,000,000. 9 point, I'm going to round this to 9.5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 9.5 times 10 to the power of 15 meters. So that is how, in terms of converting to distance, light year into meters, that's how many meters it's worth. So you'd be doing 9, 5, and then 9, 5, and then 14 zeros to get how many meters there are. So that is why we use the light year, because things are just so far away. Things are just so far away that we need a new unit of measurement. And once again, be very careful. Even though it says light year, it's a measurement of distance. It's how far light travels in a year. So if I were to say something like light minute, that means how far light travels in a minute. Light second, how far light travels in a second. Okay, right. Now for a bit of practice. So once again, I'm going to give you a quick link to some practice. Let me just, if you open that link up, let me just show you what is available. So I have 4 documents on there. You see 8L practice test higher, 8L practice test mark scheme, 8L practice test. So 8L practice test is just a standard practice test just to get you used to some exam questions. If you want more challenging exam style questions, similar to like the challenge questions on the topic test we do, have a go at the higher one. And you can mark yourself via the mark scheme. In terms of weight calculations, if you want to get used to using the formula weight equals mass times gravitational field strength, you can have a go at those problems there. The answers are at the bottom of the page. And once again, as always, if any of you are ever stuck where you're not really sure why how I got an answer that I did, or you're really confused by a particular question, feel free to send me an email, leave me a comment on either on YouTube or show my homework. That's absolutely fine. But the main key thing is just feeling a little bit confident with how you're doing. And then on the Monday after half-term break, you guys are going to see the assessment pop up for you guys to do. So all of the answers are up available for you to have a go at. And if any of the questions you're not really particularly sure how I got that answer, feel free to send me an email. Okay? So that is the end of the space topic. There's many opportunities for further research and further learning. If I could make a recommendation, there's a documentary series called Cosmos. There's an older version and a newer version. Both are good, but I mean, you guys might like the newer version. So the older version is with a man named Carl Sagan, and the newer version is with a man named Neil deGrasse Tyson. And the title of this is Cosmos. So if you have a watch of it, I think you'd really enjoy it as some easy watching, just to learn more about outer space, the vastness of outer space, because it is a fun topic. And if you take triple science, when you get to that point, if you opt for triple science, you do the space topic. Double science, unfortunately, space in detail is not part of the curriculum. So just putting that out there, guys. All right, so have a good rest of the day, and I will resume streaming after half-term break, and there is going to be an assessment after half-term break. Okay? Right, bye.